Good day, dear colleagues. My name is Sova. Allow me to introduce the presentation Identification of Unmanned Aerial Vehicles using RF Fingerprinting and Deep Learning Networks by the authors Yuriy Kondratenko, Sova, Oleksiy Kozlov, and Vitalii Kuzmenko. The structure of the given presentation is as follows: the introduction, the problem statement, the proposed approach, RF fingerprinting techniques for identification of unmanned aerial vehicles, the evaluation of the proposed approach using deep learning networks, and the conclusions. UAVs are increasingly used in various industries, such as surveillance in defense and urban monitoring, logistics, including package delivery and inventory tracking, and industrial automation, such as plant inspection and agricultural monitoring. Researchers have explored various machine learning approaches for detecting drones using different sensing methods. Such approaches include computer vision, audio analysis, sometimes even fuzzy logic systems in cases of uncertain environments. There also has been a case for data fusion systems that combine multi-sensor data to improve robustness and accuracy. However, in recent days, a new approach has been gaining traction: radio frequency machine learning. According to DARPA's definition of a radio frequency machine learning system made in 2019, such system aims to learn to recognize a specific transmitter based on the unique radio frequency fingerprint naturally imparted by hardware imperfections within that transmitter. The following slide shows our proposed approach for identification of unmanned aerial vehicles using radio frequency machine learning systems. Such method involves dataset retrieval, data processing, feature extraction using several radio frequency fingerprinting techniques, and deep learning-based classification. Next slide shows the details of the public open source dataset used in this research. The source has been provided and shown on the slide itself. This dataset was collected from two 40 MHz receivers in the range of 2.4 to 2.48 GHz, and it captures signals from three drone types: Parrot Bebop, Parrot AR, and DJI Phantom, as well as background noise packets. This dataset also includes several levels of classification. However, for the purposes of this research, we only use the drone type level of classification. As a result, we are presented with a class imbalance that we have to remedy, as well as the quite high sample size. Therefore, we have to proceed to the next step, such as data preprocessing. At this stage, we apply a thresholding technique to segment signal data into RF packets. We apply such technique only to the packets that include the drone information. Therefore, the background noise packets avoid such thresholding technique. The resulting packets are then subsequently split into equally sized chunks that contain 4,000 samples each. And finally, we use k-means undersampling to reduce background noise class imbalance. The next slide shows the equations and the algorithms for feature extraction using several radio frequency fingerprinting techniques that are rooted in digital signal processing. The first one is the power spectral density. It describes how the power of a signal or process is distributed across different frequency components. To calculate PSD, we first have to compute discrete Fourier transform. And since two receivers have been used to collect information, we are presented with a low and high band component. They both have to be used for training. Therefore, we have to concatenate them. And to ensure spectral continuity, we include the normalization factor for the high band component. The next technique is the short-time Fourier transform, STFT shortly. It splits the signal information into smaller overlapping segments and applies the discrete Fourier transform to each segment, and this results in the spectrogram, a two-dimensional array that describes the frequency content of a signal over time. However, instead of using the raw spectrogram itself for training, several other features are inferred from this representation, which are then concatenated in a single feature vector. In our case, these are the spectral centroid, the spectral flux, and the spectral entropy. Spectral centroid is a measure of the center of mass of a spectrum. Spectral flux is a measure of how much the spectral content changes over time between consecutive frames. And spectral entropy is a measure of the disorder or unpredictability in a single frequency content. Finally, the last technique used in our research is wavelet packet decomposition. Wavelet transforms themselves are a mathematical tool used in signal processing to analyze data at multiple scales or resolutions. In this work, we use wavelet packet decomposition, an extension of discrete wavelet transform. It is used to generate a flexible and detailed multi-resolution analysis of a signal. In our case, we use 6 levels on the composition. This results in 64 sets of coefficients, which are then characterized with 2 features, the root mean squared error and the standard deviation. Both of these features are then concatenated in a single feature vector passed into our models. The following slides show the architectures used for classification of our resulting feature vectors. The first one is the convolutional neural network, which was heavily inspired by the LeNet architecture. It consists of 3 convolution modules, a flattening layer, 4 dense modules, and a softmax layer as a final layer to display the classification result. 3 convolution modules each decrease the dimension sizes subsequentially for the filter sizes and the kernel sizes. And in turn, the dense modules reduce the dimensions of the fully connected layers. In comparison, the residual neural networks replaces the convolutional modules with 2 long short-term memory modules. Both of them incorporate 64 units for the hidden memory state. And 4 dense modules remain the same throughout the CNN and the RNN. The next slide depicts the parameters used for the training process. We use the adaptive moment estimation as our optimizer, categorical cross-entropy as a loss function. We carry out the training process in 50 epochs with a batch size of 32 using a learning rate of 0.01, and we use accuracy as our performance metric. Finally, it should be mentioned that we use a 5-fold stratified cross-validation for class balance during the training process. The next 2 slides depict the training results for both CNN in the form of confusion matrices and the RNN using 3 of our resulting feature vector datasets. These results are then compiled into a comparison table using accuracy and F1 score computed from the results. From what we can gather, wavelet-based feature vector and the convolutional neural network achieved the highest classification metrics of 97%. In comparison, the PSD dataset shows the worst results. The CNN is unable to determine the background noise packets, while the RNN overfits on them. The STFT-based approach shows slightly better results, however, it still fails to ascertain enough features to distinguish between different drone types. In conclusion, deep learning networks, especially CNNs, are highly effective for RF-based drone identification, and combined with wavelet-based feature extraction provide a huge increase in accuracy. In our case, 97%, which surpasses past models depicted in previous researches by 7%. This method supports secure, accurate, and scalable UAV detection in real-time settings. Future research could explore the integration of additional deep learning architectures, as well as further optimize the residual neural networks in the context of radio frequency machine learning. Thank you very much for your attention.